All right, we should know what a row echelon is, row echelon form, and basically has the staircase look where you have zeros in the lower left-hand corner of the matrix. And some additional properties to make it a reduced row echelon form is just to make sure that all your leading variables or all your leading coefficients in each row is 1. And then if you have a leading 1 in each of these rows, all the other elements or entries in that particular column are zeros. So let's introduce a couple of other definitions, and then we'll do an example, and then we'll identify the row echelon form, reduced row echelon form, and these new vocabulary words. A pivot position is located corresponding to a leading 1 in the reduced row echelon form. Now, if you don't reduce all the way, you can still identify your pivot position because it'll be the first non-zero element in a particular row if it's already in row echelon form. And a pivot is a non-zero number in a pivot position, so that's what we're going to call that particular element is a pivot. All right, let's do an example where we have 3 equations, and it looks like there's 4 unknown variables, x1, x2, x3, and x4. So let's start by making that into a matrix and then go through the process of reducing this matrix or writing it in row echelon form using elementary row operations. So let's start by transforming this into an augmented matrix of coefficients and the right-hand side vector, column vector. So we have coefficients of 1, -7, and there's x3 that's missing here. We'll call that a 0 and a 6. And then x1 and x2 are missing for the second row, and then we have x3 has a coefficient of 1 and x4 has a coefficient of -2, and then -1, 7, -4, 2. So this is the matrix. If we were to look at this as a matrix, this is the matrix of coefficients for our system, and then we want to augment that with the last column that would be the right-hand side of the system. And so in our last column, we have a 5, a -3, and 7. So this is our matrix. In our augmented matrix, we can do a variety of elementary row operations that can shuffle things around, that can switch some rows and multiply a row by something and add it to another row that gets replaced, and multiply a whole row by something. So we have a variety of different ways to, different steps to take. Does this look right? Yeah. What's -6 doing there? Thanks, Chris. Anything else? All right. So let's do one operation that would add the first row to the second, multiply the first row by 1, add it to the, not the second, but the third, and replace the third row by it. And in the first lecture, I think I was putting arrow R3 to say we're going to replace the third row, but let's just assume that whatever this is going to get replaced, it's the second R here that's going to get replaced. So R3 will get replaced. So we have 1, -7, 0, 6, and 5 for the first row. That's not going to change. 0, 0, 1, -2, and -3 for the second row. That's not going to change. And then now I have my third row that will change, and it'll change by adding the first row to that third row. So 1 minus 1 is 0, -7, plus 7 is 0. 0 plus negative 4. 6 plus 2. And 5 plus 7. So we've managed to get rid of a couple of entries in the bottom row. So it looks like we could do one more step here to get it in row echelon form. And looks like I can take the first row or the second row, multiply the second row by positive 4, and then add it to the third row and replace the third row. So if I'm replacing the third row, that means the first and second row remain the same. And then the third row is going to change. Now, the thing about this algorithm and this process is that if we're reducing the top rows before the bottom rows, then when we multiply the second row by 4 and then we add it to the third row, since the first couple of elements in the second row are already zeros, it's not going to change anything in the third row. So we know that that's going to be 0. And we also know that since we're making this move to make it in row echelon form, that the next element of that will be 0, because that's exactly what we did. That's the reason why we're doing our step, is to get rid of that next element. So 4 times negative 2 is negative 8 added to positive 8. That's also going to be 0. And then 4 times negative 3 is negative 12 added to 12, and that's also equal to 0. So we have a row of zeros, and it's all the way in the bottom. So that's the first criteria for your row echelon form. The next criteria says that if you have an element here in a row, the first element going in a row is that's non-zero, then it's going to be stacked up in that way. So we get this staircase looking thing with zeros. We can go all the way to so that's row echelon form. Do we need to take any steps to reduce it, make it into a reduced row echelon form? No. So reduced row echelon form, remember, has to have the leading variables or leading coefficients here to be equal to 1. And then in wherever there's a 1 that exists, the rest of the column would be zeros. So this is row echelon and also reduced row echelon. Okay. Now, a pivot position in a matrix is a location in A that corresponds to a leading 1 in the reduced row echelon form. So how many leading 1s do we have? We have a pivot in these two positions. So the pivot is a non-zero number in a pivot position that's used as needed to create zeros. So those are our pivots. If they were not equal to 1, then we would multiply that particular row to make it equal to 1, multiply by something to make it equal to 1, and then it would be a step closer to the reduced, and those are our pivot positions. Okay, any questions? Yes. And we have 2 pivot columns. Any questions? All right. So I think we have one or two more definitions coming. Free variables. Oh, the steps to satisfy the first four criteria is called the forward phase. To go forward in your these definitions aren't that important, but I may use them every once in a while. The whole idea of back substitution is to actually solve for that linear system, and to solve for that, we need to, set it back into the variable form into the system of linear equations. And the backwards phase is equivalent to performing a back substitution, and then that helps us solve for that system. Okay. What I do want to highlight is the idea of a free variable, which we'll be using a lot. So the variables corresponding to the pivot columns are called the basic variables or leading variables, and the other variables are called free variables. So the leading variables give us information about the particular variables that we're solving for. And then the free variables are free in the sense that we can let them equal to whatever we want to solve for this particular system. I mean, after all, we are solving for this system. So let's see. This is the same matrix, right, as the one we were working on, provided I didn't make any mistakes. So let's take a look at this system transformed back into, did it just turn purple? Let's transform it back. I don't know. No, we're going to say that we're transforming them back into a system, and then we're going to try to solve for it. Still purple? Oh. All right, so the back substitution is going to, well, not the back substitution. Let's transform this back. The first row over here will correspond to 1 times x sub 1 minus 7 times x sub 2 plus 0 times x sub 3 plus 6 times x sub 4 is equal to 5. Remember, this is an augmented matrix, and so the right-hand side is the right-hand side. And then the next one is 0 times x sub 1 plus 0 times x sub 2 plus 1 times x sub 3 minus 2 times x sub 4 is equal to negative 3. And then we don't have to write the last one, but if you do write the last one, you can just say 0 is equal to 0, which seems to be a true statement, and it looks like that will mean that we actually will have solutions. What do you call a system that has at least one solution? What's it called? Consistent. Remember that? And so if it doesn't have a solution, it would be inconsistent. We ran into a problem, say on the first quiz, where we had an inconsistent system. We got something like 7 is equal to 12 or something like that, which doesn't make sense. And so that's inconsistent. Here we ran into something, we're running into something where we have 0 is equal to 0. It seems like it's a true statement, so we have a consistent system. So the question is, what is our solution going to look like? All right, according to this definition, we have some free variables involved here. Which ones are the basic or leading variables? So remember, we pointed at the pivot columns. First and third columns are pivot columns, and so we have values, or we have basic variables in the first variable and the third variable, x1 and x3. Okay, our free variables are coming in the other columns. So we have a free variable in x2 and a free variable in x4. So how do we say that? Well, we just say x4 is a free variable. Okay? That means we can let it equal to whatever we want. And so at this point, let's just let it equal to x4. x4 is equal to x4. Or you can choose another variable like t. Let's just say x4 is free. And now, back solving, we get x3 is equal to minus 3 plus 2x4. And since x4 was free, we don't have a specific value for x4 to put in there. We'll just keep it as x4. Does that make sense? Okay, yes. Okay, yeah. Because fourth column is a non-pivot column. And so that's going to be our free variable. And when it's free, right now, we're just going to say it's equal to x4. After we solve for the rest of them, we can randomly put in a value for x4 and the other free variables that are involved. And then we'll check to make sure that it works in the solution. And it should. It better. Otherwise, we did something wrong. Yeah. Yes. So the pivot columns represent the leading variables or the basic variables, and then the non-pivot columns are the free variables. Not counting the augmented part. The last column is the augmented part, and we don't look at that. So x2 is also a free variable. And then now when we look for x1 is going to be equal to 5 minus 6x4 minus 7x2. And if we had x3 in there, we would literally put in this expression that we had for x3 in for x3. Sure. This is going to be my arithmetic police. Yes. That's what I need. Okay. So this is our solution. It looks like a funny looking solution. And when we have free variables, we can let them equal to whatever we want. So let's let x4 equal to something, and independently, let's let x2 equal to something. What? 1 and 2, for example. So this is randomly selected. But let's say if x4 is equal to 1 and x2 is equal to 2, then what's x3 going to equal to? So this is going to give x3 equal to minus 3 plus 2 times x4, which we said was equal to 1, negative 1. And then x1 is going to be 5 minus 6 times x4 plus 7 times x2, which is going to be 13. I hope. So the set of combination of numbers where x1 is equal to 13, x2 is going to equal to 2, x3 is equal to -1, and x4 is equal to 1, should satisfy the system of equations that we had from the beginning. So I don't know exactly what the original system, but we didn't change the first equation. So I know the first equation is x1 minus 7x2 plus 6x4 equals 5. So if we put in those values in for those appropriate places, where x1 is equal to 13, x2 is equal to 2, and x4 is equal to 1, we should get equal to 5. So we have 13 minus 14 plus 6. This is 5, right? Is it? I'm not getting 5 in my head. Yeah, it's 5. Okay. There's 3 equations, so there's 3 equations to check. I think the other equation looks the same as what we have. We didn't change it. So x3 minus 2x4 is equal to -3. x3 minus 2x4 equals -3. And so again, we have an x3 is -1 minus 2x4. x4 is equal to +1. And that should equal to -3. So -1 minus 2 equals -3. So that worked. Let's try the last one. -x1 plus 7x2 minus 4x3 plus 2x4. Again, my -x1, I forgot already. What is it? What? Plus 7x2 plus 4x3 plus 2x4 equals, did I get positive 7. All right, again, drop those values in for x1. That's that's 13, if we can see it better. For x2, for x3, and for x4. So -13 plus 7 times 2 minus 4 times -1 plus 2 times 1. We have -13 plus 14 plus 4 plus 2. And this is 1 plus 4 is 5 plus 2 is 7. So it worked where we randomly selected our x4 and x2 because they're free. And had we put a different set of values like 0 and 0, I wish you guys would have chosen 0 and 0 because that would have been a little bit easier, then we would have gotten another true statement here. Yeah. You could use 0, 0, 1, 1, 3, 3, same value, different values. It doesn't matter because they're independent from each other. x4 does not depend on x2, and you have 2 free variables, so you have 2 degrees of freedom, so to speak. Okay, any questions? So the idea of a free variable will be important for us. Okay. In the next page over here, it talks about parametric solutions for your equation. When a consistent system has no free variables, then there is exactly one solution. We'll see that in the existence and uniqueness theorem coming up next. But when it does have free variables, you can let the free variables equal to any variable you want, arbitrary variable. And for the sake of parametric equations, in one or two parameters where we can actually try to visualize and graph it. We can call it S and T. Call those free variables S and T. And when the system is inconsistent, then it has no parametric representation. So I'm going to go back to the previous page and see if we can write this parametrically, write it as a parametric system. So let's see if we can write this using parametric representation. And what we need is this information over here, what we said x4 was free, x3 was equal to some sort of solution that has an x4, x2 is free, and then x1 is some other written solution in terms of x4 and x3. So I'm going to write x1 first, which is equal to 5. And I'm going to reverse the order, so I have x2 first. It doesn't really matter. But just to kind of see it nicely, x2 is free. x3 is equal to, what's it equal to? -3 plus 2x4. And x4 is free. So I'll keep it as x2 and x4 for now, and then at the end maybe I'll do a little switch. But your solution set can be written as a column matrix, which hopefully by the end of today we'll be able to identify as a column vector. Five plus 7x2 minus 6x4. And then this is free. I'll leave it as x2. And this is minus 3 plus 2x4. And this is also free. I'll leave it as x4. So now what I'm interested in doing is writing it by separating these components, these pieces, with the coefficients of x2 and x4, the free variables, and then also the other constant terms that are not being multiplied by x2 or x4. Now, if I run down here and look at the constant terms of the vector, I see a 5. I don't see a constant term for the next one. There's a -3, and I don't see a constant term for the last one. So I can start off with a column matrix that has 5, 0, -3, 0. And then now I look at the coefficients of x2. I have a coefficient of x2 for the first one. That's a 7 times x2. And then I have a coefficient for x2 for the second one. I don't see an x2 for the third one, and I don't see an x2 for the last one. So it looks like I have 7, 1, 0, 0. And then a coefficient for x4 for the first one is -6. I don't see any x4s for the second element or the second position. I have a coefficient of 2 times x4 for the third one, and then 1 times x4. And so now this is in parametric form. I have my solution written in parametric form where I can easily replace the variables x2 and x4 with like s and t or u and v or something else if I need to. And to say that that's a free variable means we can put any number we want for x and x2 and x4, and we should get a solution, a set of numbers for x1, x2, and x3, and x4 to make this thing work. All right? So that's your parametric representation. Any questions? We can't graph this because it's in 4 dimensions. I mean, you can. Just close your eyes and imagine it. But if we have something in 2 or 3 dimensions, then we can definitely graph that. And we might come up with some examples of that later. But in general, you can graph this. If you have a graphing program that graphs parametric equations in 2 or 3 dimensions, you can certainly graph some of these solutions. Questions? Yeah. This one? I think it's supposed to be a 1. Yeah. Because it's a coefficient of x4, and then the coefficient of x4 is 1. All right. So, existence and uniqueness theorem. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if you have a reduced row echelon form, and you got that last row, or any row, as 0, 0, 0, and then the augmented part is a non-zero number, what you essentially have there is you have 0 is equal to a non-zero number, which would be inconsistent. So if you happen to come up with a row that looks like this, then your system is inconsistent. What's inconsistent again? No solutions. Glad you guys remember that. A system is consistent, then the solution either has exactly one solution, or it has an infinite number of solutions. So these 3 scenarios are similar to what we've learned back in algebra, when we had 2 equations and 2 unknowns. 2 equations and 2 unknowns represents 2 lines, and either the line intersects exactly at one point, right? Consistent, exactly one solution. That means it has no free variables. Or it's the exact same line, consistent, and back in algebra we also called it dependent because it was the same line. But that means we also have a free variable to represent every single point on this line, an infinite number of solutions. Or they're parallel. Which means inconsistent, there's no solution, these 2 lines don't intersect. Okay? And so what they're saying here is that we can get all that information by reducing your system, your matrix, your augmented matrix into row echelon form or reduced row echelon form. And by the time we get to reduced row echelon form, we should know exactly what's happening with our system. Okay? To actually find the solution or solutions, if they are consistent, takes a couple more steps. But by the time we've got the matrix row reduced, we should be able to look at it and say, the system is inconsistent, or this system is consistent and it has exactly one solution, or this system is consistent and it has an infinitely many solutions because there's some free variables. Okay, so those are 3 cases, 3 scenarios. The procedure for row reducing and solving for a system is written here. I'm not going to talk much about it. We've done it. We've talked about it a little bit, but I'll let you dig up the notes. By the way, you guys know where to find the notes, right? You guys found the notes from last time? I don't think I'm logged in yet. There we go. Let's pause for a commercial break. So notes and etc. It's not there. I thought it was there. It's there for my other class. All right, that's where it's going to be. Thank you. So after class, usually after class, maybe that same evening, you'll see the written notes up here. These notes, so this lecture is getting recorded, and so there'll be a video version of this as well, but that might not come until the day after because of the rendering process and uploading and stuff. So this will get populated with notes and videos and all kinds of other stuff that might come up in class or outside of class. All right, so check this. If the notes aren't here by tomorrow morning, then you can send me an email because that just means I forgot. And also, the number of emails that I get tells me how many people actually try to look at the notes. Question? It'll also get posted up here. I'll probably post it up a little higher. Well, there is nothing higher. I'll probably squeeze in another module over here. There we go. This is where you'll find it. There's nothing in there right now. Yeah. Yeah, you should be able to go into your math lab. Is it there? Has anybody tried? Chapter 0? There's no chapter 1 yet? Really? What's it about? Oh my goodness.
You don't even have to count, just in case you figure out how to do that, they have a little X there for you.
Is this what the answer is supposed to be? Yeah, never mind. They got us covered. All right, well, yeah, sorry. I thought it was all set up. I think your homework might be a little bit more challenging than the chapter 0 homework. Oh, I don't have it. All right. I got some something in my to-do list. I have to copy all the homework from a previous class. Okay, I'll deal with that. So if the homework isn't up by tomorrow morning, somebody send me an email. I'm gonna get 35 emails. If I don't have it up. Right? If I don't have it up, I deserve 35 emails. All right, let's move on. Looks like we have a couple of examples. Some of your homework problems might look something like this, where you have a system, 2 equations and 2 unknowns, but instead of you just having to solve for that, I mean, you'll probably have to just do a row reducing anyways, but this one puts a little twist in your problem, where you have to find values of h and k to make this either inconsistent or consistent with exactly one solution or consistent with infinitely many solutions. And in these examples, it's only a 2 by 2, so let's see if we can work this out. Let's do problem number 19. These problems are taken from the book, which is tricky to access too. You need to download CDF, the Wolfram program, and to view your notebooks. But it's a free download. All right, let's set this up and do some row reducing. We have some unknown variable h and 2. We have a 4 and 8 and k as your augmented matrix. And then we want to do some row reducing. So we will, looks like we could take row 1 and multiply that by -4, add it to row 2, and obviously replace row 2. So our first row does not change. And our second row will have a 0 underneath the pivot position 1. And then we'll see what else. -4h plus 8. And then -8 plus k, or k minus 8. And then we have that. Now, if we really wanted to make it a reduced row echelon form, we would have to divide this second row by this expression over here. And since it's not a nice number, let's just leave it like this. This is row echelon form already. And that's good enough to deal with. We don't have to get it in reduced row echelon form to try to see if it's consistent or inconsistent or whatever. Yeah. I think if you have dealing with numbers, just numbers, you can reduce it all the way. And then that will help us solve for this quicker. I mean, we could solve for this just as quickly, except we have to take a few more steps that's not in matrix form. So since we're in matrix form, we should just row reduce it. Eventually, you'll just plug this into the computer and do RRF and then reduce everything anyways. But for now, we're doing things by hand. So you can get an appreciation for all these steps that we're taking, all that's algebra and arithmetic. All right, let's try to handle the first scenario where there's no solution. And this is going to be inconsistent if we can get the last row to be 0, 0, and a non-zero number. Remember? So if we can get this to be a 0, 0, and the augmented part is non-zero, then we can say that 0 is equal to something that's not equal to 0, so that's no solution. And the first element is already 0, so we just want a -4h plus 8 to be equal to 0. And then at the same time, we want k minus 8 to be not equal to 0. Right? So that happens when h is equal to +2 and k is equal to not equal to +8. So the combination when h is equal to 2 and k is not equal to 8 means that we have an inconsistent solution. Now, Whoops. A unique solution. Let's do C first, many solution, because I think it's easier to deal with that first. Let's do C. Consistent with infinitely many solutions. What's the key here? Yeah. To have a free variable, right? And when do we have a free variable? In this particular scenario, what can we do to have a free variable? A row of zeros would do it, right? We have a whole row of zeros, then we have a free variable. You guys put an E for zeros, like potatoes, tomatoes. Doesn't matter. All right, so a row of zeros, that just means we want these two elements to be equal to 0 at the same time. So we've kind of solved for that already. And we just say if h is equal to 2 and k was equal to 8, then we have a row of zeros. And if we have a row of zeros, we have a free variable. If we have a free variable, we have infinitely many solutions. So a last one, consistent with exactly one solution. What happened there? Anything else? So not inconsistent. And not consistent with no free variables. So not consistent means we can't have h equal 2 and at the same time k not equal to 8. So h equal 2, k not equal to 8. And we also can't have this scenario where h is equal to 2 or k is equal to 8. So it sounds like if h was not equal to 2, it would work, right? So you want not these scenarios. So if h is equal to 2, not equal to 2, then we have a non-zero pivot here. And then are there any restrictions on k if that's the case? No restrictions on k. So k can be anything as long as h is not equal to 2. Now, if h is not equal to 2, that means this element here is not equal to 0. So we will have a number there, and you can eventually turn that into a 1. And so it becomes a pivot. It becomes a pivot. And then it doesn't matter what the augmented part is going to equal. As long as there's a 1 here that's a pivot, then that's going to give you a unique solution. So you can also state that need a pivot in the second column. We already have a pivot in the first column, that's automatic, and then just the second column, we need to make sure that we have a pivot there, which means that element has to be non-zero. What was that again? That was negative 4h plus 8. Okay. Any questions? Yes. Another make a free variable. That's not necessarily that's not a definition. It's kind of like a process, and it may not work depending on how many equations and how many unknowns you have. So it's in this particular scenario, we have 2 equations and 2 unknowns, and so a row of zeros would guarantee a pivot. So you kind of yes, it's not always a rule. The size of your augmented matrix makes a difference in what we're talking about. When to have that row of zeros rule. Any other questions? Okay. What's next? Vectors. Hey, this is blank. Do you guys know what vectors are? I always like to show this. Oh yeah, you guys already know it. I don't know if I want to hold it. All right. Well, okay. So vector has direction and magnitude. For us, we're going to look at vectors as a matrix. And in general, we're going to look at it as column vector. And then later on, the direction and magnitude business, we'll deal with that when we really need to deal with that. So where are we? I think I need to look at this. This is taking up too much space. All right. So when you first learn about vectors, you generally study vectors in R2 and R3 because there are vectors that you can actually visualize. But really, vectors exist in higher dimensions as well. And so geometrically, that's a little bit more difficult to visualize or to grasp, but there's a lot of, in physics, they sometimes use four-dimensional vectors for things. And when you're dealing with matrices, the idea of vectors in any dimension kind of makes sense for us when we're trying to solve these strange problems. The example I like to use for higher dimensional vectors, we'll get to it later, but the examples I like to use for that would be like your grade. Your grade's dependent on your homework, your quiz, your worksheets, your exams, your final exam, journal, STEM speaker series things. So depending on how many categories, I can assign a six-dimensional vector, say if there's 6 categories. I can assign each person a six-dimensional vector that would represent your grades. And if you just look at a list of numbers, that can be determined as your grade, as a vector, as a six-dimensional vector, or a vector in R6, for example. But for the sake of simplicity and visualization, we're gonna take a look at, begin looking at vectors in R2 and R3. So a matrix with only one column is called a column vector, or simply a vector. So we're gonna represent these things as column vectors. Now understand that when you're dealing with physics or with Calc 3, the idea of vectors goes beyond matrices, and you can denote these vectors a lot of other things. But for now, we're going to look at them as matrices, and then we're still going to look at them, you know, as points in space or arrows with magnitude and direction, and we can take a look at that in 2 and 3 dimensions. But we'll always come back to a vector as a column vector, as a matrix with one column. So let's take a look at a couple of examples of column vectors, U and V. So here's some notation also that's going to be added. When you look at a textbook or some written work, a lot of times, if they have the ability to typeset boldface, that's how they write vectors. But in some cases where you can't boldface, like if you're writing stuff down, you don't want to boldface the U. It takes up a lot of time to make it boldface. So instead of doing that, we usually just write an arrow on top of a variable to represent a vector. And let's put -2, 3. So we can take a look at an example of vectors in R2, and we use this R2 to represent a two-dimensional plane. We use R3 to represent your three-dimensional space. And we'll use R4 to represent vectors that exist with 4 components. But in R2, we'll use this symbol. It looks like an epsilon-like symbol. Anybody know what the symbol means? It's in, belongs to. Part of a set. Okay, is an element of. So U and V is an element or is in R2. And geometrically, we can view this as points 1, 2, and -2, 3. But vectors are supposed to be arrows with direction and magnitude, and so it's better if we actually denote those as points that connect the origin to that point, and then there's your arrow with the direction and magnitude. Okay, we could do this in 3 dimensions as well. But those are your vectors, and that's how we can possibly represent them. All right, now we have these vectors. Again, vectors can be points, points can be vectors, but just understand that I think we call it a vector in standard position because these vectors can easily move around. Right? We don't need these vectors to be stuck here, and that's kind of like one of the things that we learned in maybe in physics. I don't know if you guys do that in physics. But if you move a vector, as long as it has the same direction and same magnitude, it's not copying. It's supposed to copy and paste. Control C, Control V. Copy, paste. There he goes. So it turns out that for these vectors, it doesn't matter where they are in your geometric space. As long as they have the same direction and magnitude, then they would be the same vector. So you can move those vectors around, but it's better to look at them in standard position because their ending point, where the arrow points to, is actually that point determined by the values that are given in your components. So those are vectors. We can add, subtract vectors. And adding and subtracting vectors require component-wise addition or subtraction. That seems simple enough to handle. We add this. We can subtract them. Actually, the idea of subtraction can get a little bit messy also because usually when we're dealing with spaces and fields and different number systems, we're really just focused on 2 main operations, addition and multiplication. So the subtraction is like the opposite of addition. That's how we can kind of take care of that. But in this case, we could just get the idea of subtraction by the subtraction that we already know. Now, multiplication of vectors is a little bit more complicated. And so we won't do multiplication of 2 vectors. We will talk about scalar multiplication, which is a little bit different. A scalar multiplication says that we could take a number, any number, and multiply it times a vector. So, for example, we could take 7 and multiply it with the u vector, and that's 7 times 1, 2. 1, 2 is our u vector. And we're going to get 7 and 14. So we can take a look at the word scalar and say that we're taking a vector and we're scaling it to either stretch it or shrink it, depending if you're multiplying it by a number bigger than 1 or less than 1. But the idea of a scalar means it's something that you're multiplying by a vector and you're changing the size of that vector. It's based on the word scalar, which is the scale, or another word that we use is any constant, or not even constant, any real number that is not a vector. Because vectors, real numbers aren't really vectors. I mean, you can think about it as vector as a 1 by 1 vector, but generally we don't want to think about it as a vector. So any real number that's not a vector is a scalar. So regular numbers. And complex numbers are also considered scalars because they're just numbers. Speaking of complex numbers, anybody interested in learning about complex numbers? Complex? No. Anybody interested in learning about complex numbers? We have an independent study group that has that's studying complex analysis. You might need some Calc 3 business to do line integrals. So if you've already taken Calc 3 or currently taking it, this might be an interesting class. It's a 3-unit independent study class that's run by me, I guess. Yeah. Well, Calc 3 is multivariable, yeah. I think we meet on Tuesdays at 11:15 somewhere at the Learning Center, depending on how many people we have. We'll either meet in a desk or meet in a room. Well, if you're interested, send me an email, subject complex analysis, and then I'll send you a contract, see if you're interested. And tomorrow, it's going to be our first meeting. We'll get to meet people who are interested. Anyways, so we got addition, scale, and multiplication. Geometrically, when we add these two vectors, there's some geometry behind it. We get this idea of a parallelogram. And so, for example, this vector, this addition that we did over here, where we have u plus v, and we get -1, 5. So -1, 1, 2, 3, 4, 5, somewhere up here. See if I did this to scale. So I get this new vector that's equal to the sum of the two vectors. Now it turns out that these vectors the original vectors u and v, let's see, copy, paste, did it paste? Nope, didn't paste. What did I do? Copy, paste. Anyways, so if you take a look at these two vectors u and v and attach them, either u plus v, it turns out u plus v is commutative, addition is commutative. If you attach them, you get this parallelogram. Which one's u? U is 1, 2, so this is u, this is v. And then if you attached the u and v vector, you get the sum. The diagonal turns out to be the sum of those two vectors. And for those people who know about vectors, you know that the difference is the other diagonal of the parallelogram. And we won't talk about that. Okay? So that's the parallelogram for addition of vectors. And then one more piece of information, the length of the vector. We can find the length of the vector by Pythagorean's theorem or something like that. So this is your vector u. The length of u is the distance between the origin and the point that's given. And so the distance here is a square root of the difference of the head minus the tail in each of the x's and the y's. So 1 minus 0 squared, 2 minus 0 squared, right? And since we're always going to assume that this vector is in standard position, which means its tail is at 0, 0, and then the head, or the where it's pointing to, can be anywhere. So vector v equals to AB will have length equal to, and the length is a square root computation, which means it's going to give you a single number. It's not another vector. It's going to give you a scalar value. It's going to be the square root of a squared plus b squared, each of those components. And the length can be generalized to three-dimensional vectors as well, and for that matter, any dimensional vector. Okay? All right, so I think that's it for today. Look out for the notes and the video in class in the next couple of days, and then hopefully your your assignments will get posted soon too. All right, see you guys next time.